So let's just get right on into it. We're talking about unequal lines and angles in a triangle. And we're on Theorem 15. And I hope this is just going to be a good help to all of you who use this. And so let's just get on into it. And let's talk about Theorem 15. It says if two straight lines drawn from a point in a perpendicular to a given line cut off equal segments from the foot of the perpendicular, then they're equal. So let's just draw out what this is even talking about, and then we'll prove this theorem. And so it says if two straight lines drawn from a point in a perpendicular to a given line. So we have to draw our given line first, and we're just going to label this A, B. And it says we have to draw a perpendicular to that given line. So we'll just quickly do that here. Here we go. There's our perpendicular, and we will call this RF. Okay, so we have a given line. We have a perpendicular going to that given line. And now we have to draw our two straight lines from a point in this perpendicular that we just drew. And so we're going to draw two straight lines, and it says if two straight lines drawn from a point, so we just created a point right here on that perpendicular, and we'll call that point P, to a given line cut off equal segments. So we just, for the sake of this proof, I didn't obviously measure this out, and we don't have to, as long as our picture is close enough and we state all these things that they are equal to each other, it doesn't matter. So we just use these two lines to cut off equal line segments on that given line from the foot. This is the foot of the perpendicular. We cut off equal segments both ways from the foot of that perpendicular. The theorem is stating that these two lines will be equal to each other if they come from the same point on a perpendicular and they cut off equal line segments from the foot of the perpendicular. So we're trying to prove that this line is equal to this line. And I didn't ever label these, so let's label these points where the two straight lines meet the given line. And so we're trying to prove, over here we can see we're trying to prove that PD is equal to PE. All right, so we have enough information to prove what this theorem is stated throughout the course of this year already. We have enough information that we can prove that these two lines in this big triangle are equal, or we could talk about the individual small triangles, however we want to do it. All right, so we have our given, we have our proofs, or what we're trying to prove. And so obviously in our first step of every proof, we need to write down our given. And so we'll just quickly write down that DF equals EF, because we are given that right on up here. DF equals EF, and that RF is perpendicular to AB. All right. And then our reason we said that is because it was part of our given information. Number two, our second statement is going to be that PF equals PF. I believe most of us are going to understand why we're able to say that PF equals PF. Well, it's the same exact line. And so just with that second statement, you can probably see where we're heading here. We have two triangles, two smaller triangles on both sides of this perpendicular line. And so we probably are going to try to prove that this triangle is congruent to that triangle. And so we're going to use, because they both share the same side, it equals itself. And so we can say that PF equals PF because of identity, the identity property. All right, number three. And now that we have this side and that side equal to each other, and now that they both share the same side, which is equal to itself, we can state another pretty much obvious fact about the picture that we have here. We can label this angle and that angle right there. Instead of saying angle DFP, or an EFP, we could just now simply state angle 1 and angle 2. We know something about those two angles because of what we have been given. We're given that this line is perpendicular to that line, and so we know by definition of perpendicular lines that they form right angles. And so we could say that angle 1 equals a right angle, and angle 2 equals a right angle. And we can say, that's not number 4, this is number 3. Well, we could say that that's true because of the definition of perpendicular lines. All right. So now we know that both angles, angle 1 and 2, are both right angles. So now if they both equal the same exact thing, they both equal angle 1 and angle 2, both equal the same exact quantity. They both equal right angles. And so we can then, by substitution, say that angle 1 equals angle 2. And that'd be our substitution axiom. All right. So now we have quite a bit of information already about this picture. We've stated that this is equal to itself. We've stated that these two sides are equal to each other. We've stated that these two angles are equal to each other. And so with that being said, we can now say, because of the theorems we've learned in the past, that triangle PDF is congruent to, let me make that a little bit better, congruent to triangle PEF. And we can do that by side, angle, side. Side, angle, side. And so there we go. We've got our two triangles congruent. And lastly, we can state that PD is equal to PE because of CPCTE. Corresponding parts of congruent triangles are equal. And there we have it. There's theorem 15. If two lines are drawn from a point in a perpendicular to a given line and they cut off equal segments from the foot of the perpendicular, then these two straight lines are equal to each other. All right. Well, on the coattails of theorem 15, we came up with a corollary. And we see that corollary 15-1 states that if two straight lines drawn from a point in a perpendicular to a given line cut off unequal segments from the foot of the perpendicular, then the straight line that cuts the greater segment, and I should say cuts off the greater segment, is greater. And so let's get our proof all set up. I'm going to say statements over here. Statements, excuse the quick handwriting here. And I'm going to say reasons over here. Let's draw some straight lines. Get this theorem started. And so we have, here we go, number 1 here. Obviously number 1 on the reasons is always going to be given. We have our given stated up here on the top already, so let's write that down. RF is perpendicular to AB, and DF is greater than EF. All right, let's write out pretty much the same exact picture that we started off with last time. We have our given line. We have a perpendicular to that line. Let's label these lines real quick. A, B, this is R, F, and now we have they cut off unequal segments. So from this point, I'm going to come out here, and then to this point, I'm going to come over here. Okay, and now I'm going to label this point P, this point D, this point E. All right, so this theorem is stating that the same thing. We have a point in our perpendicular lines here, but they cut off unequal segments, so that is not equal to that. And so our theorem is stating whatever line cuts off the greater segment is going to be greater than this other line that cuts off a smaller segment. And so let's say that we've already stated that this line is bigger than this line. DF is greater than EF, and we're trying to prove that this line is greater than that line. Okay, let's talk about this. We've already stated that we have perpendicular lines and that DF is greater than EF. Kind of not a easy thing to think of right off the bat, but a way to prove this is to pretty much make equal segments on both sides of the foot of the perpendicular. That's going to help us create a proof that we in class have talked about how we can prove certain things. And so we are going to draw GF equal to EF. All right, so we would get our compass out if we actually had to, and I'm just explaining what we would have to do if we were to make this picture actually accurate. The only reason I have to do that is to show our reason why we're able to say that. We would grab our compass and measure out the size of EF, and then we would keep our pointy part of our compass and just measure out and lay off this same line segment. And so we're going to draw pretty much at a point right here, and that's not necessarily, let's try to make it as close as possible. Let's erase these arrows and label that point G. Now GF equals EF, or close enough. And so the reason we can draw that is because we can construct, we've learned how to construct in our class, construct equal line segments. All right, number 3. Now we're going to draw GP. So we're going to draw an auxiliary line from G all the way to P. Okay, and we know we could do that because we have 2 points, and 2 points determine a straight line. Perfect. So now we have an auxiliary line, and we automatically know that we know something about the auxiliary line we just drew. We know something about this. You may not realize it, but we just talked about Theorem 15, about if there's a point in a perpendicular and we draw 2 straight lines that cut off equal line segments, that these 2 straight lines are equal to each other. Well, we just constructed a line segment that's equal to this line segment. And so if we have the same point in the perpendicular and we cut off the equal segments, well, look at that. We know that those 2 line segments are equal to each other. So now we can say that GP is equal to EP. And we would say if 2 straight lines drawn from a perpendicular cut off equal segments, they are equal to each other. All right, there we go. So now we can say that that is equal to that. Number 5. Well, let's try to keep them in the same plane. There we go. With that being said, we now have technically an isosceles triangle here with the 2 legs equal to each other. And we know certain things about the base angles of isosceles triangle. Now, we have not stated that this is an isosceles triangle. We could easily state that triangle PGE is an isosceles triangle, but that's just more writing, and we don't necessarily have to state that. We can get around that. But we do know something about angle 1 and angle 2. And we know that they are equal to each other. Angle 1 equals angle 2. Because angles, opposite equal sides in a triangle are equal. All right, there we go. Also, we could state that base angles of an isosceles triangle are equal if we would have said that that is an isosceles triangle. But we don't need to do that extra step because we can reword things that way. Perfect. So we know now that this angle is equal to this angle. But we're trying to prove that this side is bigger than this side. But obviously, since this side equals that side, we could also try to prove that this side is equal to this, or is greater than this side, I'm sorry. If this side is greater than that side, then this side would be also greater than that side, and vice versa. If this side is greater than that, then this side is greater than that. Perfect. So number 6, we're going to now label this angle 3. We can say that angle 1 is greater than angle 3. Again, many of us would understand the reason behind that, because if we were now to look at this triangle right here, angle 1 is now considered an exterior angle of this smaller triangle. And we've learned theorems and corollaries about exterior angles of a triangle, and we've learned that exterior angles of a triangle is greater, or I should say are greater, than either opposite interior angles. So angle 1 would be greater than this angle, and it'd also be greater than the angle up in the top of that triangle. And we can't say anything about that angle. It'd be supplementary to that, but it's greater than that, or it's greater than that. We've also learned, and this is totally off topic, but we've also learned that the exterior angle is greater than, or is equal to the sum of both opposite interior angles. All right, so we can say that. Number 7, we could also now say that angle 3, what did I just say? Angle 1 is equal or greater than angle 3. We could say that angle 3 is less than, I'll turn it around. Angle 2 is greater than angle 3. So I just said that angle 2 is greater than angle 3. And why could I say that? I just said that angle 1 is greater than angle 3. How could I say that angle 2 is greater than angle 3? Well, previously, in step 5, we said that these two angles are equal. And if this is greater than that, then that has to be greater than that. And we could say the substitution axiom there. Substitution axiom. Just substitute equal quantities for equal quantities, and the statement remains true. All right, and then lastly, we could finally say that PD is greater than PE. And why? Well, now we can look at the macro, the big triangle, and if this angle is bigger than this angle, they're both angles in the big triangle, and we've learned theorems and corollaries again for this principle. In a triangle, sides that are opposite greater angles are greater than sides that are opposite smaller angles. So if this is bigger than that, then the side opposite of angle 2 is greater than the side opposite of angle 3. And so we could say something similar, a similar wording here, sides opposite a greater angle in a triangle are greater than sides opposite a smaller angle. And there we have it. We have just proven what we set out to prove. We proved that PD is greater than PE, and that is what we set out to prove. So there it is, theorem 15 and its corollary 15-1, stating pretty much if you go from a point in a perpendicular and cut off equal segments, then the straight lines that cut those equal segments off are equal. And the same kind of idea, if a line cuts off a greater segment, that line will be greater than a line that cuts off a smaller segment from that same point in a perpendicular. And so there it is, theorem 15 and corollary 15-1.